Hey, I'm Tomer Kaspa. The problem we're looking at today is from Chapter 13, Solutions, more specifically solute solubility in solvents. And the problem is, for each compound, would you expect greater solubility in water or hexane, and then indicate the kinds of intermolecular forces that would occur between the solute and solvent in which the molecule is most soluble.
Here's some background information that's going to help us solve the problem. Our two possible solvents here are hexane, which is a nonpolar, long-chain hydrocarbon, and water, which is a small polar molecule. The kinds of intermolecular forces we can see are London dispersion forces, or LDFs, which is the intermolecular force between nonpolar molecules, dipole-dipole interactions, which is intermolecular force between polar molecules, and hydrogen bonding, which is a special type of dipole-dipole interaction that occurs during the binding of hydrogen with oxygen, fluorine, or nitrogen. And there's also ion-dipole interactions, but we're not going to worry about them for this problem because we're dissolving the solutes, meaning all the molecules stay intact and there are no ions in solution. Also, really important is that phrase at the bottom, like dissolves like. That basically means that polar solutes will have greater solubility in polar solvents, and nonpolar solutes will have greater solubility in nonpolar solvents. That's going to be really helpful for us later on. The first solute is toluene, which is a hydrocarbon. Since it only contains carbons and hydrogens, it is nonpolar, and therefore it has a greater solubility in the nonpolar solvent hexane and only displays London dispersion forces, since those are the intermolecular forces between nonpolar molecules. The second solute is sucrose, which is a carbohydrate, meaning there are a lot of carbon and hydrogens, but there are also oxygen atoms and OH groups, which are circled in red. Those OH groups and oxygen atoms make the sucrose overall a polar molecule, and therefore it has a greater solubility in the polar solvent water. The intermolecular forces between sucrose and water are going to be London dispersion forces as well, but you're also going to have dipole-dipole interactions because of those oxygen atoms, and hydrogen bonding because of those OH groups. The third solute is isobutene, which, like toluene, is also a hydrocarbon and only contains carbon and hydrogens. Therefore, it is nonpolar and has a greater solubility in the nonpolar solvent hexane, and as well only displays London dispersion forces. The fourth solute, ethylene glycol, is also a hydrocarbon. However, it contains OH groups, which make the molecule overall polar. Thus, it has a greater solubility in the polar solvent water, and it will display London dispersion forces, dipole-dipole interactions, and hydrogen bonding because of those OH groups. To summarize, we looked at the molecular structure of each of the four solutes to determine their polarity, and thus we're able to determine which solvent they will have a greater solubility in, since solutes will have a greater solubility in a solvent of the same polarity. Also, by using the molecular structure and paying attention to specific functional groups within the molecules, such as OH groups, we were able to determine which intermolecular forces were present.